record. Alrighty, folks. So we're going to start 5.3 today. I have a tentative calendar up in Schoology for this week. I think I have it posted already. Don't really need to take the time right now, but I'm about to go do it because I don't want to be a liar. Week 2. Oh, I do have my weekly plan up there. Okay. But I goofed it. Okay. Well, I'll fix it later. But basically, our plan is to do 5.3 today, 5.4 tomorrow, and then 5.5 on Thursday. So you know what the plan for the week is. So it means Wednesday and Friday will just be work question days. All right. So you know that is coming. So on that note, let's start going on this and see how it all goes. Okay. Inversely, insert better title. I still need a better title. If you have a better, like, jokey title for inverse functions, please let me know. I need a better title. That's just not actually like part of my joke. It is literally just like I don't have a better like joke title to go along with this. But today we're learning to find derivatives of inverse functions. We'll be successful when we can use properties of functions, inverses, and inverse functions. Sweet. Attendance. All right. So there are 6 things. There's a lot of things to know, but there's 6 things in particular that I want you to know about inverses. Some of them are facts. Some of them are things that we need to be able to do and show, and there's more information with. All righty. Am I sharing? I am sharing. Okay. Hot diggity. So here are the 6 things. Oh, what's going on there? Oh, something's thinking. That's probably bad. Well, we'll see what happens. So the first one is just the fact that if a point's on F, then if you flip the coordinates around, that point is on the inverse. Remember, IFF is not me horribly misspelling if. Capital IFF stands for if and only if. The idea is that if I haven't explained it before, and we'll explain it now because I think it's important. You know, when we talk about if-then statements, like if the sky is blue, it's the afternoon. Or if it's the afternoon, the sky is blue. Those don't necessarily always work both ways. Or like if it is midnight, if it's midnight, then it's dark outside. That's true. But if you flip them around, if it's dark outside, then it's midnight. Well, that's not always true. If and only if means it doesn't matter what order you put it in, it's always true. Our official, like the most technical name for it is called a bijection because it doesn't matter which way you go on that. But that's just a fact. We use that throughout pre-calc. So that's just a fact. 2, every function has an inverse, but not necessarily an inverse function. Because there's other things that might have to go into that to make it a function. All right. So those are little things to just keep remembering and are going to be super important for us. A function has an inverse if and only if the function is 1-to-1. So this is kind of new. We never put it in these words last year. So this is slightly building on that. 1-to-1 means that each input has a unique output. Now, remember we talked about that each input has exactly one output, means it's a function. This is talking about a 1-to-1 function, meaning that each input has a unique output. So like y = 2 is not a 1-to-1 function because every x value goes to 2. 1-to-1, an example, a simplest example of 1-to-1 is y = x, or x cubed, or x squared if you restrict it from 0 and greater or 0 and less, as long as it's one of those two. So these are all just some facts to know. So number 4, a nice calculus method to show a function has an inverse function is to show that it's monotonic over an interval. Excuse me. I don't know where that came from. So that's something I'm going to spend more time talking about that. 5, the slope of an inverse function is the reciprocal of the slope of the original function at the corresponding point. That also requires a little bit more, and we'll talk about that in a sec. And the last thing, we have a couple ways to show functions are inverses. All right. So we're going to look at these 3 right now. The first 3 are mostly facts. Like there's not a whole lot to do with that, but 4, 5, and 6 are things we're going to look at and see how that all plays out. Okay. These are the things that we're going to actually spend the time to look at, play with, and see what happens. All right. So start with number 4. A nice calculus method to show a function has an inverse function shows monotonic over an interval. It would be nice to know what monotonic means. Well, if you break the word apart, mono is 1. Tonic, I don't know what tonic means, but monotonic generally means it's only increasing or decreasing on an interval. All right. That's how we can show something's monotonic. If it's increasing or decreasing, only decreasing, that sounds like calculus stuff that we've been doing for a while. How do we show that with calculus? Whether the first derivative is positive or negative, respectively. So the idea is to show something's monotonic, we just have to show that over an interval, the derivative doesn't change sign. That's it. Show it's positive, show it's negative, doesn't matter. As long as it doesn't change sign, we're good to go. So that's the big thing that you need to remember and do with this. All right. That's all there is to this one. You just literally have to take the derivative of a function and see if it's positive or negative over that. As long as it doesn't change sign over an interval, it's monotonic. Thus, the inverse on that interval is a function. All right. Number 5. So this is the one that we're going to probably spend the most time on. The slope of the inverse function is the reciprocal of the slope of the original function at the corresponding point. There's a lot of words there, and it can be kind of hard to pull apart what's really going on. So I tried to rewrite it in a slightly different way. So if AB is a point on F, then BA is a point on F inverse. So the derivative of F inverse at B is equal to 1 over F prime at A. That is what this is saying. And that's kind of the formula that we're going to try to remember. And use a couple times. This shows up on the AP test a couple times, and I'll show you a sample AP question that uses something like this. So here's just an example I have. So what I did, here's F prime, here's G prime. F and G are inverses, right? -5, -85, -85, -5, -2, -7, -7, -2, 1, -1, so on. So right here, I'm going to look at the F prime of -5. F prime of -5 is 50. 1 over 50 is 0.02. Note that's G prime of -85. Because remember, the point -85 is on F. So the point -85, -5 is on G, the inverse. And at the corresponding X value, so -85 here, or -5 here, 1 over F prime of -5 is equal to G prime of -85. Boom. Again, that's the big takeaway. That's like the thing that's going on. Which, as we keep talking about the fact that you swap everything around for the inverses, it's kind of all makes sense. This is another way you could see that. Sometimes it's written, the rule is written like this. And it's not always super clear that the X and the Y belong together. They're paired. They're from an order pair. That's not always clear. So I'm trying to point that out by using the tables and different things. Here are the two functions that I used. Are these the two functions I used? Oh no, the green and the purple lines. These are the equations of the tangent lines at the respective points. And here's just a graph. It's really hard to see the important things here. But there's a link when you come back to look through this. It's a Desmos calculator you can play around with, and you can see how everything's connected. So here's a sample AP question. So let f be a differentiable function such that f of 3 is 15, f of 6 is 3, f prime of 3 is -8, and f prime of 6 is -2. G is differentiable and is the inverse of f. So what's the value of G prime of 3? So we got a couple options. So let's take a look and see which one it could or should be. So I want G of -3. So let's annotate. Looking at my options, G of -3, that's corresponding to this one right here. So what this is really telling me is what's 1 over f prime of 6. Because the 0.63 is on f, so the 0.36 is on G. So f prime of 6 is -2. So I want 1 over -2. My answer is A. All right. So that's that one. 5, 4, 3, 2, 1. Cool. So here is a link to, it's a Khan Academy thing. They have a bunch of practice on this idea. Again, I'm spending a lot of time on this, but this is usually one question on the multiple choice. And that's it. So I feel like I'm spending a lot of time talking about this one thing, but it's kind of one of those, like, here's the final thing about inverses that we really want you to know about how that works. The fact that you can find a slope at an inverse without even knowing the equation of the inverse. Or if you have your original function doesn't give you an inverse, or it's really hard to come up with what the inverse is, you can use that property to kind of help you out. Again, oh yeah, I can talk about that. Remind me at closure, I will talk about what the in-person test looks like, usually every year. So I don't anticipate it's going to be that much different if we're going to be doing it in person this year, but I'll gladly tell you all about that at the end of class. I'm almost done. I don't have much more. All right. 6. We have a couple ways to show functions are inverses. So geometrically, we could show that they are reflections of each other over the line y equals x, which again kind of all follows with a lot of the things we've done. Numerically, if xy is in one of them, then yx must be in the other. Again, that's this first bullet point, so you can verify their inverses that way. The numerically way, that's a fact that once you know their inverses, it must be true. Or if you find a point on one that's not, that the flip is not on the other, then they're probably not inverses. So it's a way to check that things aren't inverses. This one's really not as good for proving things are inverses. But once you know they are, or you're trying to show they're not, this is a good way to like determine that and kind of work with from there. Algebraically, we do it by composition. So here's the notation that we typically use for composition. F of g of x or g of f of x equals 0. We need to show both things. Now, that's not the only way we show that. We also show it by typing it out like this. That's how we typically did it in pre-calc, and that's the way most people start off doing it. It just as you start getting into calculus and math beyond like Calc 1, this first notation tends to be used much more often than the other ones. So why? I don't know. Because it's literally less to write would be my guess. Like, I'm kind of joking on that, but not really. A lot of the time we start using more a bunch of different symbols later on in math because we're writing so many different things that we're just gonna jot shortcuts where we can. It's called being efficient. But again, both these two light circles points, they mean the same thing. You do need to know both notations. The AP test could use this for the notation in black, or it could use the notation in white. Switch and solve is fabulous for finding inverses, but if you're going to verify inverses, that's not good enough. You must use composition to show inverses. As a person, I hate saying there's only one way you may do something, but if you're asked to verify inverses, like on a free response or something, and you do it by switch and solve and not by composition, hashtag 0 points. Like, there's particular things that are expected of you at certain times. And while I try to give you as much freedom as possible, that's one thing I need you to be able to for sure do. And you'll get practice in that in today's assignment. But that's it. Notice how it's inverted. Your graphing calculator can help you do some of this too. You can draw, there's a draw inverse button on your calculator using Algebra 2. If you can go back and find that, it's helpful for sketching, but it's not a required thing. Here's your practice for inverses. It's due soon, very soon. All right. Oh, there's one more thing I wanted to show you. So there's a bunch of stuff. I have some extra things here that really aren't super needed. Here's an example of composition if you really want to go spend some time and just kind of look through it because you need an example. Here's a picture I did on the board, I think last year, of seeing how the derivative of the inverse is reciprocal of the original function at the corresponding point. You can see that there. There's more examples. Here's a Desmos activity that is an investigation. The second part of it's an investigation about inverses and derivatives. If you want some more practice beyond the Khan Academy thing, here's a thing. I made a link for it so you can go join that if you'd like. You don't have to. It's just that if you're like, man, I want to spend like really get this, here's another thing that you can do. All right. So that's what I have for you today, folks. Stop and recording.